Are you going to be going to go to the pub afterwards? Are you up for going to the pub afterwards? I'm not going to volunteer. Because I gather they tend to go to the pub afterwards. So, yeah, well, yeah, if they're going, yeah. Good evening, ladies and gentlemen. Good evening, ladies and gentlemen. I've just been waiting a mo because we've got quite a number of people online, and it was only fair to them that we started at the appointed hour, 6 o'clock. Fortunately, we haven't got to go back a month. It is a typo on the screen there. Thank you for pointing that out. Somehow there's a gremlin on the dates on some of the slides. But a warm welcome to you all from the BGA and the Engineering Geology Group of the Geological Society. My name's Stephen Jeffries, Chairman of the British Geotechnical Association. So welcome all here and welcome to all of you online. This evening we have a presentation on Wylfa Power Station by Victoria Edmonds and Dr. Matthew Free. But before we go there, I should just say no fire alarms are expected tonight. So if there is an alarm, it is real. The emergency exits are back there or the front there, and you may occasionally hear rumbles underneath from the Underground Railway, so that's been ever part of the Geological Society, so that's nothing new. There's a signing in sheet going round, so if you could sign that in just so we know who's here, and we will probably adjourn to the Blue Post pub afterwards, so just so advanced warning of that. Now, our speakers for this evening is going to be split into two halves, roughly 30 minutes each. Victoria Edmonds, who is a senior engineering geologist with Atkins, graduated with a degree in geology from the University of Bristol and an MSc from Imperial College. And prior to joining Atkins, she had extensive experience in site investigation and consultancy in the UK and Western Australia. Lucky you in Western Australia. And she currently works within the energy geotechnics sector, which has been involved with infrastructure projects in the UK and overseas. And she's been part of the Wylfa project since 2014. And going straight on to Dr. Matthew Free, he's director of Arup, and he leads the Arup Natural Hazard and Risk Management team for the UK MEA. He's a chartered scientist and a chartered geologist with over 27 years' experience of working on major infrastructure projects worldwide. And he's worked on large multidisciplinary teams taking on large projects around the world. So with that, I'll pass straight over to Victoria. There will be time for questions at the end, and you must use the microphone for the questions for those online to be able to hear. Thank you all. Victoria.
Hello everyone, good evening. My name's Victoria, or Vix Edmonds, and as was said, I work at Atkins. I've been working on the Wylfa project since 2014 and was on site for a good few months doing supervision of the site investigation works. I've since been involved with some of the interpretation of the geotechnical parameters. I will generally be talking about the ground investigation, the techniques we used, some of the data we gathered, and I'll also go on to discuss the rock mass classification we designed specifically for the Wylfa project. This will lead in to Matthew talking about some of the seismic aspects of the site. So a rough outline, I've got about 40 slides, talk about 25 minutes, 30 minutes, give a brief background to the project and the objectives of our rock mass classification scheme. There'll also be a brief fly-through of our 3D model. So the Wylfa site is located in Anglesey in North Wales. There is an existing power station there called Wylfa A, and which is currently defueling. Since sort of about the 80s, there's always been a plan to build another nuclear power station there. So there's been various phases of ground investigation. But most recently, from about 2009, Horizon's been kind of ramping these ground investigations up to really get to the detailed design level. So I'll be talking about the investigations that have happened since 2009, but more in detail since 2014 when Atkins became involved. The plan in the top left gives you an idea of the structures that are being planned, so 2 power blocks, some auxiliary buildings, backup buildings. There's also some marine structures. In this current location, there are 2 glacial drumlin hills that will potentially need to be removed, and a lot of rock excavations, potentially 30 meters thickness of material that needs to be removed. A lot of that bedrock, which is why we really need to understand the bedrock and the geotechnical parameters that are happening there. This slide provides a little more detail on the layout. We're looking north. There's the existing Wylfa A power station in the top left. You can see the turbine buildings, the backup buildings, and so the marine structures are on the left of the slide. As with all large projects, there's a lot of participants here. So Horizon being the scheme developer, and they own the site. Hitachi are the main technological designer. Atkins have been brought in as the geotechnical consultant, with Arup being the seismic hazard consultant. And there have been many other people involved on this as well. Sorry if you don't all get a mention. So the ground conditions that we have at site. There's generally glacial deposits overlying low-grade metamorphic bedrock. The most recent glaciations that affected the area were the Devensian from 10,000 years ago. The low-grade metamorphic bedrock is generally of sammites and phyllites, which used to be mudstones and sandstones, laid down in a marine environment. There's a lot of faulting and folding that's happened on the site. The image in the bottom right gives you an idea of two theoretical boreholes, and if you try to interpolate between them, the sammites and the phyllites, you'd struggle because of the lensing and the folding and the faulting. So it's really difficult to link the lithologies throughout the site, which I'll come on to a bit later with our rock mass classification. Generally, the bedrock on site is of good, consistent quality, though. So the superficial deposits, the image on the top is a schematic which was done for previous works, but it shows you the drumlin material that we have with kind of clay lodgement tills, and then there's granular basement tills. The bedrock as well is quite variable. There's some steps in it where the glaciers have caused sort of rutting in the bedrock top. Some quite deep depressions. These are really quite localized. You'll find them in one borehole, and then 20 meters away, rock heads maybe 10 meters different. So the glacier deposits, as expected, very variable. The image on the bottom right is taken at the coastline, so we have some quite nice exposures. Shows you the high quantity of gravel and cobbles that are in there. So you can imagine that taking some undisturbed samples was actually very difficult. In all the investigations we did, that was 15 kilometers worth of core, I think we got 10 U100 samples. Really wasn't a lot. But at least we had the coastal exposures to give us an idea of what the material was actually like. So this slide gives you an idea of the different qualities of rock, I suppose. So the phyllites on the top and the sammites on the bottom, both, as you can see, very good core, 100% recovery pretty much. There's not much difference in the phyllites and sammites, really, in terms of geotechnical properties. So as I'll discuss later, we end up with this rock mass classification that kind of lumps them in together. Now, on the north of the site, we have a different lithology, the Guna group, which is very chaotic. You get a lot of different clasts. So we've got breccias, quartzites, basalt, limestone. The slide on the bottom left shows how large some of the clasts can be. So you can get them millimeter size, you can get them tens of meter size. The rock we were coring was generally quite similar to the New Harbour group, because it is still phyllites and sammites dominating, but the quality of the rock is a lot poorer. It's thought the Guna group was laid down as an olistrum deposit, so a very large submarine landslide that is like a breccia, so really quite chaotic. We've got many faults and intrusions that have been identified on site. Most are trending sort of northwest, southeast, and are quite vertical. Matthew will be talking more about the faults later on site, but as you can see, there are quite a few cutting across our site that have an impact on the geotechnical aspects. This slide just summarizes sort of some of the available data, and the next few slides will give you an idea of the quantities as well. So there's been 6 ground investigations since 2009, with about 450 exploratory holes, pushing nearly 19 kilometers worth of rock core. The picture in the top right is the warehouse that Horizon has hired to store all the rock core. This actually has 3 investigations worth in it, and I think the earliest 3 investigations are still actually to be transferred in there. They're in shipping containers on site. But it was an excellent facility to actually carry out the rock logging. Those of you that do ground investigations on a small scale in the UK will be quite used to just having no warehouse and you're out in the exposed air. So this was quite a luxury, and it really did benefit the quality of the logging and the core photos. There was a lot of in situ testing and lab testing as well. and we're still doing the interpretive reporting at the moment, so it's ongoing. So the first investigation really of this most recent phases was the preliminary site investigation in 2009. Only 11 rotary holes, but they were quite deep, they're about 100 meters deep. Then the intermediate, they did intermediate onshore and offshore. CH2M was heavily involved in this and gathered quite a lot of data, and they did a lot of lithological geotechnical parameters studies. Then we moved on to the detailed onshore investigation, which is where Atkins and myself became involved. This was the largest investigation in Europe at the time, it was thought, and actually went on to win the Ground Engineering's Award for Ground Investigation of the Year in 2015. Looking at the numbers up there, you can appreciate that it's quite a large investigation. We were on site for 9 months, and the initial reports took about 9 months again, but to be honest with you, in 2017, we're still writing another revision of that same interpretive report, so it's ongoing. Then most recently, last year, we were on site again for about 3 months. There was an offshore investigation, which the bottom image is of, and there was another onshore investigation that was focused on the seismic aspects of the southern part of the site, as they were slightly lacking in data for identifying some of the potential faults in the area. So the next few slides are sort of just a lot of pictures of some of the ground investigation we did. Cable percussive drilling. I think you all know it, and it's quite archaic, but to be honest with you, it still kind of does the job in getting some SPT values for us, potentially getting some U100s, which we didn't do so well on. But it meant we could use the SPT values, Atterberg's PSDs, for our geotechnical parameters. Sonic drilling was thought about, but political and money reasons, I think it was decided against. Rotary drilling in the onshore, a lot of inclined boreholes to try and pick up the near vertical fractures and faults. We had at one point 18 drill rigs on site, so there was a lot of logistics when a rig was moving every day, or quite a few rig moves a day. Admittedly, the holes were quite deep, so sometimes it would take 3 weeks to drill one hole. But using the GeoBore S, so you didn't have to take rods in and out all the time, definitely helped on that. Offshore drilling, we had 2 jack-up barges doing a near-shore investigation. Quite successful, really. We had the weather window. As you can see at the bottom, it was quite sunny for a while, so this was actually quite successful in terms of downtime. Trial pitting. I think most of you know standard trial pits. They're usually quite cheap and cheerful and quite easy to get a few done in a day. However, Horizon, being a nuclear site, health and safety was paramount. So doing a trial pit is officially working at height. So we had to show to the client and health and safety advisors that we could prevent anyone falling in the trial pit. So someone came up with the idea of using a Youngman's board. So you can see the sort of scaffolding on the right here. So that was tied down, and then the engineer was allowed to walk onto it and log from that position. Relatively effective, but you can imagine moving positions for trial pitting was quite a slow process when you had to get a tractor to move the Youngman's board. But it satisfied the health and safety for the site, so we got it done. In situ testing, so a lot of sites you might do one of these tests or a couple of them, but it's quite rare you do all of these tests in a ground investigation. So it was quite sort of a learning curve for a lot of people. You might have read it or had a lecture on some of these tests, but doing them in practice, slightly different. Surface geophysics, it was great. The client allowed us to do 3 different types of techniques. So we had seismic refraction, surface wave ground stiffness, and electrical resistivity over many kilometers, 6 or 7 kilometers, I think, worth of geophysics lines. It meant that we could do comparisons between all the different data sets, pick up anomalies, really help with identifying rock head levels across the site, interpolating between boreholes, finding depressions in the rock head levels, and using it for our seismic velocity assessment. A magnetometer survey was done, I think, back in 2010, so before Atkins got involved, but very useful, A, in finding the igneous intrusions, but also cables. And I think it helped with the seismic assessment generally as well, but it does give quite a clear image. We had optical wireline geologging on basically every hole that didn't collapse on us, which was the majority we managed to get it on. We flushed the holes very carefully, and where we could, left the holes to settle for 24 hours or so. And it meant we could get very clear images. So you can see on these three, you can really pick out the significant discontinuities and lithological changes. It really helped us identify in the core where there might be drilling-induced fractures and where there were real fractures. We also did fracture picking from this so we could get orientation data of all our discontinuities, really helped the structural geology analysis. So this is a list of the full set of wireline geologging we did. The image in the top right is from the optical geologging, and the bottom left is the setup that the specialist had on site with his laptop so he could get the images in real time, and if there were problems, he could pick it up and adjust if anything was needed. Some of this data we used on site, so some of the fluid data we used to help identify where we were going to undertake packer tests and hydro tests. Other parts of the data, like the seismic data, we had to wait for further interpretation and use it back in the office. This is the downhole seismic testing. So the image on the left is the contractor getting data on the vertical waves. So they were hitting a plate with a sledgehammer, hitting the waves going down. The middle top image is getting the shear waves. There's a wooden plank underneath the 4x4, hit metal plate on the side, and then the shear beam can shift side to side, and you get some shear waves going down and are recorded down the borehole in intervals. Cross-hole seismic testing, quite a headache on site for drilling the holes. So you usually either drill it in an L shape or a cross shape, and quite often the holes are at 5-meter intervals. Because our rock was so strong and had a fast velocity, we ended up increasing the spacing to 10-meter spacing. So you can imagine if you've got holes at 5 to 10-meter spacing, you don't want them crossing. So our holes were 100 meters deep. So it meant when drilling, the drillers had to try and make sure they were in 1% verticality of their inclination. Wasn't always possible. Some of them ended up at 3%. But as long as they weren't actually crossing each other down the hole, this was acceptable. It did cause us quite a few headaches in drilling and re-drilling some of these holes, but we got there in the end. High-pressure dilatometer testing. So the top two images are where the kind of packer and balloon deflated on the left and then starting to inflate on the right. Quite a few problems because we wanted to do a lot of the tests in the more fractured ground as well as the better quality, but it meant that sometimes the arms of the Chinese lantern got damaged. The bottom left image is some of the damage. And in the worst case, the balloon inside, which is filled with oil, would sometimes puncture. Luckily, we had environmentally degrading oil, but it was a hazard for site that ideally we didn't want to be puncturing this cost-wise and time-wise as well. Again, we managed to get the results, but it was quite a slow process. Permeability testing, we did variable head tests in the superficial deposits, and then packer tests and hydro tests in the bedrock. Quite a lot of these, maybe 5-meter spacing down particular boreholes. It was a stipulation that there were going to be electrical transducers put below the test zone, in the center of the test zone, and above the test zone, so we could check if there was any 3D flow and that the packers were actually holding the test zone pressure as required. This meant we could get images like the bottom graph. So the green and the blue lines, I'm not sure if you can see them, are holding steady pretty much, and that's above and below the test zone, which is what you want. You want the pressure to be constant there. In the middle of the test zone, for a packer test, you do 5 different pressures, and you can see there's quite clear steps on where we achieved the pressure, held it for the test, and increased the pressure. So it's quite nice having that confidence in our tests, because I've done packer tests on other sites, and you don't have these electrical transducers, and it's a bit of guesswork as to whether your test zone is really holding the pressure. Core logging. These images are what Structural Soils did for the detailed onshore investigation. We had a dedicated area for taking core photos, which really made a difference because we refer back to those core photos all the time because they're such good quality. Structural Soils did the logging on a P-logger, so a digital tablet. Meant every evening the loggers could be uploaded to a GINT kind of file, and we could have the logs within a day of them being finished rather than having been handwritten and potential errors being transferred. Really did help with quality checking. Just an image of the core photo showing you the good quality that we were able to achieve on site. And again, the core logging facility, just giving you an idea of the quantity of core, was really quite a lot. Imagine logging all that. So the second bit of the talk, I'm just going to go into the rock mass classification scheme. So I think a lot of you would have heard of the rock mass rating or the Q system that are used a lot when you have bedrock. Each of these has 6 input parameters. So kind of strength values, spacing of discontinuities, groundwater orientation discontinuities, stress reduction factors. Although we could have used these, we felt as though 3 or maybe 4 of those parameters we didn't have a very good hold of on site at that time, partly because the client and the designers hadn't finished the design. They didn't necessarily know what depth or loadings they were going to have in the buildings. We also had to use previous site investigation data, so we couldn't then ask anyone to come and record extra data that we could for the detailed onshore investigation. So we decided to modify these and sort of come up with our own site-specific rock mass classification to give an idea of where the poor and the good quality rock was. We went through various options, but we came up with using just 2 input parameters: fracture spacing and weathering grade. Fracture spacing, similar-ish to RQD, but it just gives that extra level of detail where RQD can actually miss some of the spacings that are given. It's not really fine enough detail. And the weathering grade, this is sort of for the rock mass and not just the discontinuities. We did some trials, and it was looking like using just these 2 parameters, it gave us a good handle on where the poor quality and where the good quality rock on site was. By using 2 parameters split into, those 4 weathering grades and 3 fracture spacings, we came up with a 3x4 matrix, so 12 sort of subgroups, which would be too many to sort of get your head around in an interpretive report. So we grouped them together and ended up with 5 main groups. They got called X groups just because X is a generic term. So we have the 5 X groups. Look at the colours here, because you'll notice in later slides. So the green is generally a good colour, good quality rock, and the purple and red is the poorer quality rock. A slide just giving you an idea. So the top photo is what we generally are finding as good quality, only slightly weathered, maybe fresh, fracture spacing of more than 60 mil. Bottom photo is moderate to poor quality, so less than 60 mil spacing and is moderately to highly weathered. We could then take this and put it in using AGS data into Holebase and then link it to our lab tests, and we could see that the table on the right with the UCS tests, as you'd expect, our X1 and X2 group, the good quality, would have a higher strength than the X3 and X4, and that fitted with our lab tests, luckily. So we moved that into all our other lab tests, so density, porosity, seismic ratings. It links throughout our whole report. The table on the left gives you an idea of the proportions. So most of the rock on site, about 90%, is what we're counting as good quality. About 9% is moderate, and only 1% really is very poor quality. So once we had our X groups, we could put it into a 3D model. We could then link the optical logs, the core photos, 3D model, and then Arup's 3D fault model that will come in later. And you could see there was quite often a correlation between where the faults were and the poor quality rock. And now we've got a video fly through, hopefully starting in a minute. I'm afraid those of you online won't be able to see this. So there's the borehole sticks, with the green being the good quality and the red and purple being the poorer quality. We've got the blue, which is the fault planes. There are some fault discs in there as well, and there's some igneous intrusions, which are the purple kind of planes. The red square in the middle is an approximate location of the buildings. We've also added in topographic contours, groundwater contour levels, and we're going to add in more of the lab testing kind of related parameters later as well. But this gives you an idea of what we could achieve, and people can turn the layers on and off, and for the client and the designer, it really helped them understand where on site their poor quality and good quality rock was. And going forward, this 3D model will be taken forward to use with other designers and other contractors. So I think hopefully I've shown you that it's possible to take a large volume of data and efficiently kind of analyse it and present it in a way that people can get an idea and an understanding of the bedrock, especially on a site where generally we just have New Harbour Group, and you could just put it all together as one, or you could try and split it into samites and phyllites, but for geotechnical parameters, we found that this was the most efficient way of presenting that data to other users. We've got a 3D ground model that we're still continuing to develop, and Horizon's been very good at facilitating all the different consultants on site using the 3D model and adding to it. And with the rock mass classification, we've used it successfully on the New Harbour group that I presented here. We also used it on the Guna group that I mentioned on the north of the site. We took the same parameters and just recalled it. We called it the G groups because they were slightly different strength and geotechnical parameters, but having the boundaries of 60 mil and 600 mil fracture spacing and the weathering grades still work the same in breaking up the rock mass. Thank you for listening, and we'll have questions at the end, but this just gives you an idea of the large number of people that have been involved in the project. So thank you, and I think Matthew will be on.
Good evening, everybody. I'm Matthew Free. I've been involved in the project since 2010, which is a very long time, 7 years now, which is a good, just over a quarter of my career, which is a worrying number. Okay, so I'm going to be talking about the seismic hazard assessment and particularly the capable faulting component of that, and I'll explain what that means. So our scope of services, Arup and the BGS team, is divided into three main components. We do the probabilistic seismic hazard assessment of the ground motion, so that's the amplitude of the ground shaking. We also do the tsunami hazard assessment, which is the seismic waves or waves from other sources. We also look at the capable faulting assessment, which is the geological faults at the site, which has been introduced by Victoria. Just interesting scale effect here is some of these images, looking at the regional scale, in the order of 1,000 kilometres across. So, 10 to the 6 metres. The bottom image, one of these scanning electron microscope images that I'll describe later, is microscale, and that's 10 to the minus 6. So it's quite a huge range of orders of magnitude that we've been dealing with. So I'll start with the definition, very important, capable faulting, and I suspect many of you have not had to deal with the definition of capable fault before, and there's some very important issues here that I've highlighted in red because I don't expect you to read the whole slide. But when you're doing a capable faulting assessment, you have to identify the evidence of past movement or movements on the geological fault. That sounds obvious and everybody would be okay with that. The movement is at or near the surface, and that's very important because we're not concerned when it comes to a capable faulting assessment of faults that are at depth. Now, they're initiating at 10 or 20 kilometres depth. We're concerned in a capable faulting assessment whether they propagate all the way to the surface or near to the surface, and that's a big differentiator. It's a separation between active faulting, which can cause earthquake and ground motion, and one that can cause rupture at the surface, so that's a very important distinction. The other issue I've highlighted there is the age over which we have to consider the assessment. And if you're in an active tectonic part of the world, if you're in Japan or California, New Zealand, where I'm from, you might consider a time frame of in the order of 10 to 12,000 years. If you're doing a very detailed study, as for a nuclear power station, you might extend back 2 million years, and that would be as far as you'd go back. When you're in a stable continental region like the UK, the current tectonic regime is much longer, and the international guidance is that you should extend back to the Pliocene. So we're going back 5.3 million years. This issue of what is the current tectonic setting or current tectonic regime extends even further back in the UK, and it's considered to go back 8 million years. So it's a very long period of geological time that you're trying to deal with. So What is the current tectonic regime then? What's the situation since the Pliocene, 5.3 million years or approximately 8 million years? What we've got currently is we've got this northwest-southeast stress direction. That's very important, indicated by those red arrows, and that's driven by the North Atlantic opening, Iceland growing, and the Mediterranean fault boundary. And that's what's causing this stress orientation. So before that, we don't have to consider as the current tectonic regime. So we're not looking at stresses that would be driving faulting in the area before this time. And there's a tricky thing that goes on here with regard to the cause of earthquakes, and that is the ice that occurred in recent glaciations, which Victoria described briefly, that there was ice cover. And the weight of the ice and the removal of the weight of that ice has also been inducing earthquakes, okay? But that is considered to have been finished. It finished, as we know, 10,000 years ago or so, and is not considered to be currently driving tectonics at the Anglesey site, which I think is a reasonable assumption. Okay, so now sort of defining what the problem is then, we have to go to the site, look at the geological faults, and we have to come up with something that constrains the age of the geological faulting at the surface, at the site. Okay, so it's at the surface and it's at the site. And there's a difficulty here, which Victoria briefly described, that the age of the rocks, the bedrocks, is very old, about 400 million years. And then everything else has been removed by the glaciation, and the next layer is about 10 to 20,000 years old. So it's very difficult to bracket an age to say that something has happened within the last 8 million years or 5.3 million years, because there's no strata in that age range at all. It's 400 million years, then 10,000 years. Nothing to bracket the age. We're a little bit lucky that there was these igneous intrusions that Victoria mentioned, the dikes cross-cutting the site. There's a picture of me standing in front of one of these igneous intrusions, and they happen to be in the order of about 45 to 55 million years old. So they're not great in terms of bracketing the age either, but they're better than 400 million years. So a lot of effort was put into looking at the cross-cutting relationships between the geological faults and the igneous dike intrusions. Okay, and I'll discuss that a bit later. Okay. When we are planning a capable faulting assessment study, we always start off with a 3D geological model. So everything right from the beginning, desk study, etc., started from coming up with a conceptual geological model. That was always our starting point. And so the desk study information would go into the 3D model right from the beginning and gets interpreted in a conceptual geological model. And we're doing at regional scale, which is out to hundreds of kilometres, and we're doing it at site-specific scale, which is in the boundary that Victoria described. And we're looking at all the previous ground investigations. So those are ground investigations going back to the 1960s for the Wylfa A nuclear power station site, compiling them all into our database and putting them all into the 3D model. We also take as a starting point the interpretations that have been done by others, because there was the same type of seismic hazard assessment, capable faulting. It wasn't called the same thing then, but it's essentially the same. It was done in the 1960s, prior to the first nuclear power station at the site. Then they're done regularly after that, and it was done by the Seismic Hazard Working Party, it was done by the BGS, and we took all those interpretations and put them into our model and used that for the planning and specifying and then the interpreting of our own ground investigations, which were undertaken by Atkins and CH2 and Halcro before that, etc. And we've been doing that since the preliminary ground investigation for the current site. Then we do our own interpretations of the geological fault planes, which I'll describe, and we have to come up with our own geological fault model and put ages to those. So that's the process that I'm going to describe, and it's sort of in two parts. So we have a 3D geological fault model, very similar to the one that Victoria's described for Atkins, where we put everything in, all the ground investigation information, boreholes, inclined boreholes, trenches, lots of geophysics, which I'll show in a later part of the presentation. And we also added in the coastline geological mapping shown by these different coloured polygons. Of particular interest in something that I'd like to point out is these red discs which are shown in there. And what we're doing there is we're trying to highlight the locations of geological faults which are identified in the core, and I'll show you some examples of those later. And then part of our process to come up with our geological fault model is to correlate between those locations across the site. So we correlate across from the borehole locations where we've identified faults to the coastal mapping, between the geophysics, to the trenches, and we come up with an interpretation of the location and alignment of the geological faults. We also have a video which we'd like to run. And it shows, we've taken out the sort of the regional scale stuff so we can race into the, in the interest of time, race into the site scale. So you can see we have the mapped geological faults. That's the existing power station. You start to see all the borehole information in those discs. This is these fault planes, and the discs are what we provide to Atkins for inclusion into their model. You can see these different coloured discs and their alignment with the faults, and that's the process that we go through. There's also some geophysics information which Victoria described in the model, and we correlate between the boreholes, the trenches, the coastal mapping, and the geophysics, and so that we can come up with a geological fault model which is fact-based. They're all based on observations in boreholes, exposures on the coast, interpreted when it's geophysics, and we were able to come up with this type of model. So now I'd like to describe in a little bit of detail how we do that correlation, and just show you for one example, a major geological fault which we identify that runs across the site, happens to pass underneath the existing Wylfa nuclear power station site, so quite important. Highlighted in blue is the area, length of the fault, where we're saying that we can correlate between direct observations. So where we've observed the fault by eye on the coast and logged its orientation, its width, etc. on the coast, that's one location. Where we locate it in a borehole, so we see it in the core, observe it directly, and then we see it later in another borehole, we correlate between those. That's showing us a solid line on a map and solid in the model. And then when we correlate between geophysics across the water, for example, we do it in a shaded colour or dotted inferred fault at the surface. So there's solid when we've observed it, dashed, or a lighter colour when we interpret its, the continuity of it. So one thing that you come across when you're working in the nuclear industry is the need to document everything very carefully, and it's sort of orders of magnitude more detail required than any other industry that I've been involved in. And I don't want to go into the detail of the ground investigation works, because Victoria's already done that, but this very important part of the process that we've encountered is to document everything so that each aspect of what you're using to interpret the alignment and the age of the geological fault is all put together in one place, so that somebody else can independently come along and verify what you've done or come up with an alternative interpretation. And this has been very important to us. So we've been doing these things that we call the geological fault data sheet, and it has what you'd expect, a map showing the location and alignment of the fault, the extract from the 3D model with all the points where the fault is defined, all the locations where there's ground investigation information related to that fault, going back through all the phases of ground investigation that Victoria described, actually right back to the 1960s, all that information, the core logs, the core photos, all the information, and then there's actually the 3D model of the surface itself is provided. So we give it in terms of its coordinates, depths, etc., for the capable fault plane that gets handed across to Atkins to add into their model. And the reason we do it this way, because if somebody else comes along, does another ground investigation point and finds another location where they can more accurately define the geological fault, it can be added to the model, and that can be done by somebody else. So with nuclear facility work, you have to be ready to hand everything across and somebody else takes over in 10 years' time or 20 years' time, and so we're preparing for that. Part of those data sheets, we're also providing all the core photographs, all the locations where the faults are shown on the core photographs, all the televiewer information which Victoria described, so that if alternative interpretations are to be made, they've got the information on which to do it. Because we don't want somebody else to come along later and say, where was that information that you used to come up with the interpretation of the geological fault? It's all summarised, it's all provided, so somebody can easily go and find the information. So, once we've gone through that process, we end up with what we've called the geological fault map. So, one of the deliverables for the project has been to come up with this map of what is the location and alignment of the faults, and Victoria's already described it very well. And we end up with a relatively large number of mapped geological faults that cross our site, and they happen to cross underneath the existing power station as well. And therefore, we can say that there is geological faults at the site, and they're significant, and they're of regional scale. So the very key piece of information is to say, have they moved in the current tectonic regime? That's the bit of information that we have to do next, and that's the next part of the presentation. So, when we're trying to communicate this, we always fall back to our conceptual model. And as Victoria described, we've got a 3D model, we have the conceptual model, and it's quite easy to communicate to people that if you've got a site boundary, you've got these faults passing through it. Nobody is trying to say that there isn't geological faults at the site. It's clear that they're there. What we're trying to do with the conceptual geological model, however, is try to make it simple, because we're talking to decision makers who've got a lot of other issues to consider, and what we want to get to is what are the key facts in a simple diagram, and that's this. It's got down to there's faults, there's these igneous dike intrusions, and there's a geological boundary between the New Harbour group and the Guna group. And it's harder to get simpler in a geological model than three things on a legend, I think. Okay, so the next stage of it is relating to the age dating of these geological faults. And when it comes to a capable faulting study, this is more important, actually, than the rest of the mapping stuff, because now we're going to be able to say, we know there's faults at the site. You'd expect that because of a 400 million year geological history that you're dealing with. But what you've got to be able to say is, have those faults moved within the current tectonic regime? And little flow chart here to say how we went about that. We got to the stage where we've got our geological model. We now specifically look at the core where there's geological faults identified, and we've got the breccia and the clay gouge related to the faulting. We look at what are the cross-cutting relationships to get the relative ages between the faults and other discontinuities, the igneous intrusions, the veining that occurs at the site, so we can come up with a relative age of different phases of deformation at the site. Then we specifically identify the material that's within the fault gouge and sample that for age dating, which is work that we did with the British Geological Survey. There's some specific detail of how we go about that, which involves breaking down the clay into different size fractions, which I'm going to describe in quite a bit of detail, and also what was the provenance of that clay, which is very important. And I'll describe each of those aspects in the following slides. Okay, so this part of the presentation is dealing with the sampling of the fault gouge from the borehole core now. So just sort of for the ease of the flow of presentation, I'm selecting slides which come from particular boreholes, and it's that particular fault plane of interest that crosses under the Wylfa A site, and it's in close proximity to our site. And we have a system for locating where the fault gouge samples are from, identified by stars here, and then we say, what is the borehole number, what's the sample number, and what fault is it coming from? And that's how we track the dating of the fault gouges. Important here is that we've sampled fault gouge from all the different orientations of geological faults, and there was typically 3 to 4 sets of geological faults, and there was a geographic coverage that we had to ensure that we did. So it goes from the samples are taken from the north of the site all the way through to the south. Okay, and then prior to the samples going off to the core store, which Victoria described, there's a period when they've just come out of the ground, they're undisturbed, and we have the opportunity to describe the fault gouges and look at the cross-cutting relationships before the potentially get disturbed by movement to the core store, etc. And this work has been undertaken with the BGS, and there's been a lot of time and effort gone into coming up with these descriptions of the fault gouge and the cross-cutting relationships that can be identified. A typical fault gouge at the site looks like this, and briefly on either side you can see this New Harbour group, dark grey bedrock material. This is the stuff that's in the order of 400 million years old. You can see it's broken up quite substantially, and then in the middle portion you can see that there's some fault breccia. It's completely broken up, so you know that fault breccia comes from the bedrock. And then in the middle there is a greyish coloured gouge, a fault gouge, which you can say it's pretty clear that the provenance is going to be, it's broken up, even finer material from the sides, but some of it can come from a different provenance, which is it grows in situ. So some of the clay will be orthogenic. It's growing in the fault gouge itself. And this is very important for the next stage of what I'm going to describe for the age dating. So if we're going to do these relative age dating, we repeat that process of looking at the core in hand specimen level to come up with these simple cross-cutting relationships to say what is younger and older, just typical geological field work actually at hand specimen scale, and you're doing it in microscope scale as well. So just in this image, just in very general terms, we can see that there's a material that is the broken up myelinite type rock, which has the MY symbol on it. So that's the older stuff. That's 400 million years old. That's going to be the oldest part. Then the basalt dike intrusion, B, has intruded into it, so it's younger. Okay, so we've got one cross-cutting relationship. And then there is a quartz vein, which crosses both. So that's the next youngest, obviously. And there is smaller veins which also cross-cut the quartz vein. So that's 4 phases of deformation just there, or 4 phases of activity going on. So that's 4, just in this one hand specimen and one slide under a microscope. And then you repeat that process over and over and over again for lots of observations, and you end up with at least 11 phases of deformation. So things have got very complex because now we've got 11 phases of deformation, and that's expected because you've got 400 million years of geological history. And there's a very important thing to decide to do now, which is not worry about all the earlier stuff, but only worry about the last phase of deformation, because it's the last phase that you're worried about to bracket the age of the geological faulting. And it's one of these decisions that has to be made at a certain stage because there's as much benefit in doing all your effort in understanding what is the last phase of deformation as opposed to spending a lot of time unfocused on the other 10 phases of deformation, because the bit that you're after is the last phase of deformation. That's a very important decision to make early on. So that's what we did. And going from microscope hand specimen down to thin section and polished section, we're now going down to scanning electron microscope level. So we took the samples of the clay gouge to look at it under scanning electron microscope, work done by the BGS, and what they identified, as you can see in the clay gouge, striations, telling you that movement has occurred, and many of you will be familiar with this aspect of geological faulting. You see these striations, that's what's an indicator of the movement, that displacement has occurred on this, and we're looking at the last phase of deformation. What is harder to see is that these, in the zoomed in section, which is it's pretty small, I think it's saying it's 10 microns there, so you're zooming in a long way. Remembering that a micron is a thousandth of a millimeter, so we're zooming in a long way on this when we've got a scale of 10 microns there. But what you can see is there is these white clay particles that are growing on the surface. Okay, so now you've got striations, and over the top of those, there's clay particles have grown. So they've grown in situ on top of the striated surface. Okay, so now this is very key because that's bracketing our age. They've grown since the striations. Okay, that's very important. So we've now got something that brackets the age. But they're a couple of microns across, which means it's quite difficult to investigate further. So the next stage was actually we need to take some of the samples and go take them away to do some age dating. So we're going to have absolute age dating. And so we had to do some mineralogy, looking at what the clay minerals actually are in the gouge. And what we found was that the majority of the samples were the clay at this very small micron level, only 2 micron size and less of clay, was dominated by illite clay. And it's in the order of 75 to 90% of the clay in the clay gouge was illite. That was ideal, actually, because illite has a lot of potassium in it, and you can use the method potassium-argon dating, which is quality assured. Laboratories around the world use it, lots of experience, and ideal for the project. The eagle-eyed amongst you will notice that there was one sample that had a low amount of illite in it and a larger amount of smectite clay. And smectite is not suitable for doing potassium-argon dating because it's an interlayered clay and you can't separate out the bit that's got the higher potassium in it. It mixed and it gives you very difficult to interpret the results. And we made a critical error at this stage, and we chose not to do age dating of that sample. And we went off and did the dating on all the other samples, and it proved to be quite problematic, which I'll describe a bit later. Okay, so now we've got the illite clay, ideal for potassium-argon dating, and in the nuclear industry, of course, there's going to be a huge amount of effort going into now the quality assurance and the contractor selection for who's actually going to do the potassium-argon dating. So we had to go out to all the universities of the UK that do potassium-argon dating, and we had to go further afield. And we ended up selecting the CSIRO in Australia, which was they were selected because of their ability to handle the amount of QA that's required in the nuclear industry, which I'm sure Victoria can talk at length about. So they were able to do all the QA activities that were required. They had all the test standards documented. We arranged a large number of samples to be sent to them, and we also arranged to have some blind tests in amongst the samples. So we sent additional samples, which from the same materials, but they didn't know where the sample had come from. So they didn't know which it was going to match up with. So they were blind tests. And the results that come out, which are shown on this figure, very interesting and extremely repeatable. So the blind tests indicated that we could have in the order of 2 to 2.5% accuracy going back to hundreds of millions of years. Okay, so you end up with doing potassium-argon sampling on these different size fractions that you've broken down in your illite clay. You send them off to the laboratory, the results come back telling you that the clays of different size, they're all clay size, but they're of subfractions, are of quite different ages. And there's a good reason for this, which I'm going to come on to, but there's also fantastic science just in here, because you've ended up with the age of the clay which is related to metamorphism, for example. Illite clay gets produced by low-grade metamorphism. So we've ended up having a scientific result which tells you what is the age at which the old clay at the Wylfa site was metamorphosed. And there's phases of metamorphism, and they all come out from this age dating. Not specific to our capable faulting study, but it's fantastic science, and it was very, very interesting, very excited in our team to see these results. Okay, but one of the very most important things that come out of it is the youngest ages that you get for the finest clay particles, which are those ones that grew on the fault surface, are coming out at in the order of 40 to 50 million years. So the youngest clays at the site in the fault gouge growing on those striated surfaces are 35, 40, 50, 60 million years old. So very important results. Okay. And then you need to convince yourself that what is the provenance of those clays of different size fractions. And you need to be quite convinced now, because I've showed you an image from a scanning electron microscope, and you see those fuzzy white images crossing the striations, and it's reasonably hard to be convinced by that. It's easier when you see it in 3 dimensions under the microscope, under the scanning electron microscope, but it's hard to convince people when you show that image. Even a presentation like this, I say it's like that, but it's hard to convince you. But if you go even further and you look at scanning transmission electron microscope images, and so you can really see in more clarity these clay particles of very small scale. So we're getting down to sub-micron scale clay particles, which we're trying to convince people that they have formed after the shearing and the formation of the clay gouge. And in my view, that image that is the most zoomed in one, where you can see there's a black particle, which is a clay particle, and it's the shadow of it, actually, but it's dark and well-formed. That is a clay particle that is formed, it's come from the wall rock, actually. That's a bit that's broken off the wall rock. It's old, it's well-formed. The bits that you can see growing off the edge of it, those very fine particles, those are the smallest, with the youngest age, and as a geologist, I can look at that and I can say there's no way that has been sheared. It's just not possible that a fine filament like that has been sheared. So it's grown in situ in the fault gouge, and we know its age, and it happens to be older than 38 million years old. Okay, so that's a really important observation, and to me, that is something that you can say is indisputable. I just cannot imagine a case where somebody would say, I believe that has been sheared. You can't see it. But, of course, you can't just rely on that. You have to do it by an alternative method as well to prove that that is the case. So then, not only do we do it by scanning electron microscope or scanning transmission electron microscope, we then go and we say, okay, what's an alternative method that would be independently verifying the origin and provenance of these clays? And quite widely used in other parts of geoscience is using the X-ray diffraction peak ratio method to look at the crystal structure. And when you're doing X-ray diffraction, many of you will know you're shooting down the X-rays and they bounce off the lattice of the crystal. And the simple story is that if you have an older clay particle and it's had a very long time to form, the crystal structure is well formed. So it's in nice layers, all organized, and the X-ray diffraction peak that comes back is therefore very narrow because it's all parallel, all aligned, well formed, because it's had a long geological history to do that. In this case, it was hundreds of millions of years. Clay particle is formed by metamorphism, and it gives that strong peak. And those are the detrital particles, the bits that have fallen off or been brought in from the wall rock, the old stuff. And it gets referred to as 2M1 crystal structure, but that's clear that that's a detrital particle and it's old because the lattice is well formed. And then these orthogenic ones that have grown in situ, they're younger, so the crystals have had less time to form, they're more irregular, and you'd expect the X-ray peak to come back more broad. And they get referred to as simpler, or 1M, and that's exactly what happens. So the very fine particles are the younger orthogenic formed in situ ones, and the older particles turn out to be the detrital ones with a good crystal structure. So we've used two different methods, entirely independent different methods, to corroborate this piece of evidence, which is very important. And then we plot those up, and what we do is we look at a number of the samples of the clay gouge under the microscope by two different methods, side by side, and we look at what is the proportion of these clay particles that are coming from the wall rock, the detrital ones, what's the proportion that comes from the orthogenic ones which are grown in situ, and we want to find the place, the very small particles that are all orthogenic, they've grown in place, and we work out the age of those. And you can plot this up on a nice graph, and they happen to work out in a very nice straight line all the time. And you can see that these older detrital ones, they can go back as 300 million years, and we've got the ages of those. We can find the ones where there's no longer any detrital particles, and they're 90, 95, 100%, the orthogenic ones that have grown in situ, and we get these ages which are in the order of, the youngest I think was 38 million years, but they're generally 45 to about 75 million years. So that's a fantastic result. And then when we compare the two, we can get fantastically consistent results. You know, this is one example, but it's consistent with many others, that the two different methods would give us 55 million years and 56.7 million years. It's quite, you know, strikingly good results. Okay, then we plot those up of where we've got those age dates from different parts of the site. So you can see, as I showed in a figure earlier, we took the samples from right across the site and from faults of different orientations, and we consistently get these youngest ages are pretty old actually. Then they're in the order of 35. The youngest was actually 38, but there's plus or minus a couple of million years, and up to about 75 million years old at the site. So the very important conclusion that you can make from this, that we've done the geological fault map, there are geological faults at the site, we've done the absolute age dating, which is to constrain the absolute age of the last displacement on these geological faults that are at the site, and what we find is that the ages that we're restricted to, there's nothing younger than 38 million years, okay? And when we repeat that with the XRD peak ratio method, just a different method of interpreting the results, we got 49 plus or minus 10 million years, so the minus part would get you down to 39 or so. And you can see the upper end, 70 million years versus 74, also very accurate. So for Horizon, who are developing the nuclear power station at the site, the big conclusion in red is that we can definitively say there has not been past movement or movement of a recurring nature on the geological faults at the site within the current tectonic regime, remembering that the current tectonic regime was in this order of 5.3 to 8 million years. So we can definitively say that. So that means the geological faults at the site cannot be considered capable, and that's the finding that you want to get from a capable faulting study, and that's the result. I've talked a lot, and you can't do this type of study without a huge team, and there's been a hell of a lot of people working on this project, and just to acknowledge many, as Victoria was able to do, Horizon Nuclear Power team, they have a large team, and there's a lot of effort going into this project from a lot of people. The Arup and BGS team, and just calling out a few of the Arup people, because there's a very large number of people involved from the leadership of our team, but a few people I would like to pick out. Ben Gilson, who's been working on the project with me for many years now, but there's a large number of other people. Field work I did was with Jason Manning. Jason and I have been doing the mapping along the coast with David Schofield from the BGS for 7 years now. It's a lot of effort has gone into going back and forth out to there. It's been very important for us to be working with the BGS, and throughout the cooperation that we've had with the BGS, the consistency has been with David Schofield, actually. David's been involved right from the beginning, so like to acknowledge David in particular. And there has been, we're doing seismic hazard assessment, but there's a huge amount of other organisations working on the site, and it's actually the same people that have already been acknowledged by Victoria. So, it's been a pleasure working with structural soils. It was Halcro, CH2M, Atkins, now with lots of positive interaction on the project. And we've had a lot of interaction with the Office of Nuclear Regulation and their expert panel and independent peer reviewers, as you get in the nuclear industry. So all acknowledged. Thanks very much.
Well, thank you. Thank you very much indeed, Victoria and Dr. Free. We have time for questions, but we need to put the microphone on. And that little red light has to be on. Right. Questions? I think perhaps Victoria and you'd like to come up front. Questions.
Hello, my name's John Arthur. I have a question for Matthew, taking us back to the macro scale, although I've learned an awful lot about micro as a geophysicist. On that 3D video image, you showed many faults which were connected by fault planes, but there were also disks which weren't connected by fault planes. Was that because the picture you're showing us is an intermediate picture, or that you did not feel that these were continuous faults?
It's a combination of those things, actually. There is other phases of ground investigation going on, so it will be updated, so we can always say it's intermediate, and the current phase of ground investigation is being interpreted now, actually, so there will be changes, so it is still regarded as intermediate, and it gets updated each time, so that is definitely the case. And then the faults that we show connected, as good observation that you could see, there is it's necessary to be able to say what observations do we think that we can correlate, actually, because there's going to be plenty of complexity there that perhaps we will find out later when they do the excavation, and we will find more. But we feel that the scale of the features that you can definitely identify comes across reasonably well, because you could map it through the different phases of interpretation that you have. So when we've been able to correlate a fault, which has to be of a reasonable scale to cross the entire site because it's kilometres, we have found that we do that first interpretation in one phase of ground investigation, and then quite considerable amounts of new ground investigation come in, and what we find is we cross-cut the same faults. So you start to build up some confidence that you're identifying the important geological faults at the site. But it's a very complicated rock mass, 400 million years of geological history, and the spacing of smaller scale geological faults is meters scale. So there's going to be plenty of smaller observations, and what we're trying to do is correlate what we've major is what we're looking at. Yeah.
Hi, Ray Hobbs, consultant. The inclined boreholes, did you monitor the actual inclination, and if so, how far off did they go relative to the target orientation? We
did monitor it as part of the wireline geologging suite. They do have a tool that can measure the inclination accurately. I think you get it centimetres, you basically get a constant line result. The tolerance in the specification was 3% for most of the holes. For the cross-hole seismic, it was 1%, but I think the cross-hole seismic, that was 1%, they definitely made 3%, and 3% for the rest of the holes, I think they generally made 5%, approximately. So it wasn't too bad, but you'd often find there'd be a kink, so it would be good, and then suddenly they'd hit some kind of feature, and the borehole potentially would divert slightly. I mean, it's minimal, really. So it wasn't necessarily constantly going off at a slight angle, sometimes hit off, but you can get, the contractor would have been able to give us a full 3D kind of spiral of how the hole went, but we ended up just getting a single line with a plot of what percentage it was out. But it was very useful.
John Hudson, Imperial College. I had a question for both speakers. When you're doing a site investigation in a rock mass, it's usual to measure the in situ rock stress as part of the investigation. But I don't think that you did that. And also from the second presentation, it seems that maybe we don't need to know what the in situ stress is, but when the mid-Atlantic ridge is pushing with about 20 megapascals across the country, you get it's increased in some places and decreased in other places, as would happen within the fractures within the rock mass you're talking about. And so there could be regions in there where the stress is very high, as it's being concentrated by the discontinuous geometry. So could you address that point that you don't know what the in situ stress is on the site, but should you know the in situ stress?
It has been suggested as part of one of the specifications for a ground investigation that maybe we should measure it, but it's not obviously the easiest to measure. I think money, it wasn't included in the investigations we've done to date. It potentially might be included later, but no, I agree. At the moment, we haven't tested it, and we've taken literature and whatever examples we can to provide a value, but we don't have a site-specific value.
I can add a little bit to that. Yeah, you're not the first person to ask that question, of course, because fault reactivation has been a question that's come up. And the logic for why it hasn't been done at the moment is because if the faults were if the likelihood of the faults being reactivated at the site was high, why hasn't it happened for the last 38 million years? And that's the logic, because it hasn't happened within the current tectonic regime when that stress has been in place for many millions of years. So the logic is that if you test the age where it hasn't happened, the likelihood of it happening must be extremely low.
I understand. Thank you.
Michael de Freitas, which follows on from this actually, for a question for Matthew, and that is you have shown that the site contains many faults, and you've made the point and reminded us that we have glacial tectonics, so we've had a period, but your youngest movement is 38 million years.
For these particular ones, yeah.
Yeah. How do you reconcile this? How did you reconcile this difference? Because
it's reasonable in many parts of northwest Europe. There's observations where the removal of the ice has resulted in rebound, which has had seismic events related to it. So it was an issue that had to be investigated. So I didn't talk about it in detail because we've got 25 minutes to talk about a study that we've been working on for seven years. So it's a good observation, but it comes back to, again, this, we just have to look at what is the age happening, the last age when these faults have moved at the site. And what that is indicating is that the removal of ice at the site itself has not caused movement on these geological faults. And we do it with 35 samples, age dated, on the faults of all different orientations. And we were specifically looking for this issue. If it had happened, we would have been able to explain it, that there was some post-glacial rebound and this is why it had happened, but it just doesn't appear. But it has occurred elsewhere in the UK, of course we know that, but just not at the site or in the site vicinity.
That's Gustav from Arup. One question for Victoria. It's about the classification system. One of the reasons we have the classification system is to categorize the rock based on the quality, and another one is to use them for the estimation of rock mass properties. So my question is if this system can be linked with existing systems like the GSI for the estimation of rock mass properties. Thank you.
So we have within our report, linked it specifically to GSI, because we've done a lot of rock mass strength kind of calculations using the GSI system. I think, if I remember the name, there's a Japanese paper where they do take the GSI chart and they actually quantify it, because the standard GSI chart is qualitative. There are papers out there that have a quantitative geosci chart. We've used that, and we have plotted within our reports the geosci chart, but with sort of areas where X1 would fit, X2 would fit. We have also, as part of the report, there's an outfall tunnel is one of the structures, and being a tunnel, we have provided Q rating for that specific area, but to be able to provide that for the whole site, it wasn't felt reasonable to be giving RMR and Q values to that level of detail. It could be taken forward once the final design's been finalised. The specific areas, if they want a particular rock mass rating, that could easily be brought in. This was very much a big picture for the whole site. Where is the poor quality rock? Where is the good quality rock? And doing something that was quite repeatable, robust, and could use historic data as well as our current data. That answers it.
May I ask a question to Matthew? And what evidence did you use? You made a statement to say that isostatic recovery had effectively finished at the site and was no longer occurring. We've had some presentations recently about the London Basin demonstrating it really is quite active. It's almost bobbling around. And yet you've got what appears to be a totally static site, unaffected by Irish Sea ice, Welsh ice, hasn't moved at all. What evidence have you used to come up to that conclusion?
The evidence that I'm referring to is the movement on the geological faults. So it's the sampling and the age dating of the gouges in the faults themselves. Because what is the key to it is that what we're trying to do is have these faults at the site moved in the current tectonic regime. And if you can just sample from the faults themselves, identify that they haven't moved in the last 38 million years in this case, then you've answered the question. And it's being able to simplify it down to what is the aspect that you need to answer, and that's it. Because that is a capable faulting hazard assessment, is have the faults moved within the current tectonic regime? The answer is no, because we sampled them and we did the absolute age dating, and that's it. Because there can be a lot of complications. You could say, I'm not sure that somewhere else there might have been some rebound and it might have caused movement on a fault. Yes, it's possible, but it hasn't at the faults at the site. Absolutely hasn't. Yeah, and that's the trick.
Stephen Jeffries, a further question to you, Matthew. I think you threw out a sort of throwaway remark about the smectite.
I forgot to say what that...
And so I thought, where did that take you? How did that trip you up?
Glad...
What's been happening for 250 million years to get probably 1,000 unit layers of clay crystallising that it couldn't have done in 25 minutes? I don't quite understand why it takes so long, but let's start with the smectite.
Yeah. So they're getting back to that smectite one. Thanks. It's to do with the... as you have done, you raised the question. What we did was we said we were selecting samples, and we knew that we had to do age dating, and what methods could we use to have accurate age dating. You couldn't do it with the smectite clay. Yeah, it's a problem. So what we did was we selected all the faults which had the illite clay in them, which is a bit of a fatal error, because then what you're doing is you're missing out the one that doesn't have the illite clay in there. So your argument falls down because somebody immediately, like yourself, comes back and saying, well, what about the one with the smectite in? And we got all the way through our first phase reporting, submitted it to the independent peer reviewer, and that's the question they came back with. What about the one with the smectite? So we had to do another study, which was to connect that particular fault, which had the smectite clay in it, to other locations where we had illite clay, and then know that we had done the testing of that somewhere else, and which was the case. And we had the smectite clay probably because it was nearer the surface, and the weathering had resulted in it being broken down to smectite clay rather than the illite.
Do you know what happens over the 250 million years to get that difference in peak height? Sorry, I should have used the microphone.
More than saying that it has time for the lattice in the clay to become more regular. To be honest, no more than beyond that. The crystal structure gets better and better defined with age. Yeah. The person who made the observation is Tony Milodowski at the BGS. So if anybody wants to know the pure answer to that, I can put you in touch with Tony Milodowski.
Any other questions? Very quick question. Josh Bradley, Mark MacDonald. Is this sort of level of detail done on all of the nuclear sites in the UK and Europe?
Better be.
Is it the only one?
Yeah, we hope so. Yeah.
Yeah. Okay.
Yeah. I think this is the level that's required. And just as an observation, one thing we didn't have the opportunity to discuss is the difference on nuclear sites is the level of collaboration that you have to have as well. And you notice that well, for example, Atkins and ourselves might be competitors elsewhere, but when it comes to working on a nuclear site, the collaboration is distinctly better. There's a lot of opportunities to work together, and it goes very well, and everybody's willing to share information. I think it's because of the nature of the project, being a nuclear project, everybody is focused on getting the answer right and is willing to share everything. It's going to be in the public domain, so you share everything, get it right, and you don't want people to be questioning you. Thanks very much.
Well, I think, thank you very much indeed, Matthew. Thank you very much indeed, Victoria. An amazingly data-rich environment. How do you preserve your sanity? I don't know, against the QA system. I don't know we need much go beyond that. But just before we close and perhaps move down to the pub, I thought I'd just take you through some of the coming events, mainly for the BGA, but 8th of March, EGGS meeting. Do you want to say something on that, David?
Speakers from Fugro is looking at some of the developing glacial and quaternary models for offshore, particularly the offshore environment and ground investigation. So again, 5:30 for a 6 o'clock start here on the Wednesday, 8th of March.
Grand. That's your one. We've got a few to go through. Next, 9th of March, geotechnical engineering in the coastal environment, presentation by Mark MacDonald, Peter Phipps and Lucy Wiggins. We haven't got the names up there, but mark in your diary. That one's at the ICE. Then the Rankin lecture. Landslides seem to be very much in the lecture circuit at the moment, and Eduardo Alonso will be giving a very full description on that from the University of Politecnica of Catalonia. 5:30 at the Imperial College for the Rankin lecture. There is a dinner after that. All tickets are effectively sold out for that dinner, so if you haven't got one, I'm sorry, they're sold out, but there will be probably a pub meeting somewhere alongside, to say the least. Cooling prize competition for the younger measures is being is being hosted by the Northern Geotechnical Group. We have 4 finalists, so 21st of March if you're in Newcastle. One back to you.
And then on the 19th of April, at the Geological Society, we've got Professor Jim Rose, once at Royal Holloway College, who's going to be talking to us about aspects of quaternary landscape change. So we're carrying on our glacial and periglacial working party theme, looking at aspects of quaternary engineering geology. That'll again be at Burlington House, again with 6 o'clock start.
Brilliant. One more for you. We're doing
Athena Livesey, WSP, we're talking about some of the engineering construction and the widening of the A1 up in Newcastle, up at Tyneside, and again that'll be our May meeting. Hopefully we'll start to be able to share our meetings calendar a little bit more with the BGA, so you can start to see what we're actually doing in terms of the engineering group. Now that sort of the communication is improving.
And mainly for the younger members, but putting something back, the BGA has a fund giving out support for returning mainly into the geotechnical area, geological studies. Generally anything associated with supporting younger members to get back into the profession or continue field work or work generally, up to about £1,000. Closing dates 31st of May, 30th of November. Just mark it in your diary, and when something comes up, ask, because we have a certain amount of money and we want to make sure that what we raise actually at the Rankin lecture, its donations at the Rankin lecture dinner, is handed back to the profession. So we've got a little bit in at the moment, but do ask if you've got something. I don't say you'll necessarily get an award, but we would like to make sure that any money we collect is dispersed properly and to deserving candidates. Engineering in Chalk conference coming up in 2018. background to this is we had a major European conference on soil mechanics and geotechnical engineering in Edinburgh 2015, returned a very substantial amount of money because it was an amazing success, and that enabled some seed corn funding to have about a biennial conference of the geotechnical community hosted by the BGA, and the first of those is going to be engineering in chalk. Martin Preen is leading the charge on this. Where's Martin? Somewhere at the back there. Martin, well done. Is there anything particular you want to say on that?
Well, just to say the next slide, the call for abstracts.
That's the crunch, isn't it?
And we have had our first abstract, which is quite a milestone in any conference. Submissions through the website, but we are looking for people in practice or academia to submit. Specifically, there's a theme on case systems engineering projects. Also, in younger practitioners to submit, they'll be quite short papers, 6 pages is sort of what we're going for, but posters as well. And so we are very much looking not to have people of mine and Steph's age, no offence, Steph, but we like to have younger practitioners there too. I went to the last chalk conference in 1989, my first professional conference, and I still, refer to some of the stuff there. So if you contribute by writing a paper and then attend yourself, I feel it will really help you in your career in the coming decades, hopefully.
I apologise for those online that you won't have got that, but basically it's on the BGA website. I forgot to pass the microphone to Martin. Entirely my fault. My apologies to you online. How many are online at the moment, do you know? Was that 10 or 100? 40? 40, yeah. 30. 30. I'm getting there yet. 30 online. Not bad. It's very impressive. Thank you to those who've been listening online. I hope you've been able to hear. If you haven't, do feedback. And then for those not online, unless you happen to be online very locally, it's a move down to the Blue Post pub, which David is.
We adjourn to Blue Post, which is if you go follow the Ritz, and it's the first left past the Ritz, so it's the Blue Post just at the back of the Ritz.
Before the Ritz.
Before the Ritz. So we have splits before the Ritz. Sorry, you can do before or after. It's just at the back of the Ritz. So the Blue Post is where we normally go after. So unfortunately, unlike the BGA, we don't have any sponsors for this evening, so you'll have to buy your own rounds. That's the only downside. So,
sorry about that.
Please do join us down there.
Well, thank you, Victoria. Thank you, Matthew. And thank you also, David, for hosting us here. And thank you for all of you coming. And a safe journey home, or see you shortly in the pub. Thank you all very much indeed. Actually, it's amazing how good it turned out. Yeah. Nothing to do with me. I just say that the